what we have seen till now: FM, modulation and demodulation. What are the four methods of FM demodulation? One is
PLL.
okay, and second,
So frequency discrimination.
frequency discrimination, FM to M conversion. Third, ये दोनों को हमने थोड़ा सा elaborately पढ़ा है, इसलिए you remember these two. The third one is phase discrimination,
Zero crossing.
and the other one is
Zero crossing method.
zero crossing method. So these two I have provided you the videos. For these two I will make one, or I will tell you in the class. Okay. So now our question is, if you want to send two signals, either by angle modulation or by amplitude modulation, so and you want to send these two signals over the same channel, how would you do that? So the question is, a communication medium, you want your communication medium to be shared by 2 or 3 multiple users. So if this is the bandwidth of the channel, you divide these two bandwidths to two sub channels, and you allocate each channel to each user, right? So there, if for example you have two users or two message signals M1T and M2T, and you want to transmit it over the channel, so what you can do frequency division multiplexing. Why are we calling it multiplexing? Because you are multiplexing, or you are providing the channel two signals over the same time, but the frequency bands are different. So if this is your message M1T, you upconvert it, or you use in AM or amplitude modulation. And if this is the magnitude spectra of your M1 signal, so how would the spectra of modulated signal look like? So this is the spectra of your modulated signal centered around FC1, and if this is the bandwidth, so you can transmit it, this signal, centered around FC1, and the bandwidth is B. And at the same time, if you want to send another signal M2T, whose bandwidth is B1, so you can upconvert it, or you can use a frequency, you can use a carrier of frequency FC2. So this signal will be, the spectra of this modulated signal will be centered around FC2. And if FC1 and FC2 are sufficiently far so that the spectra of your message signal 1 and the spectra of your message signal 2 does not overlap with each other, then you can easily reconstruct this by putting a band pass filter at the receiver. So this is called frequency division multiplexing. So if this is the, and at the receiver, what we do, we demultiplex the signal. So these two signals are coming over the same channel. At the receiver, you put a band pass filter centered around FC1, and the second band pass filter, which is centered around FC2. So it will, the output of this band pass filter will be M1T, and output of this filter, this band pass filter will be M2T. So this is called multiplexing and demultiplexing process. So a communication medium can be shared by more than one channel of signals or more than one signals. And this process is used to you this we use this process so that we can effectively utilize the capacity of available channel, and this is called multiplexing. So this is one method of doing multiplexing, that is called frequency division multiplexing. So similarly, you can use multiple signals and you can first translate it to different frequencies, FC1, FC2, FC3, FC4, and then at the receiver you will put a band pass filter and you can reconstruct it. ठीक है? Of course, this will not be exactly M1T, but this will be the modulated signal, right? So this is not M1T actually. This is the, if you are using amplitude modulated signal, then it will be XAMT corresponding to your message M1T. And this will be amplitude modulated signal for corresponding to your message signal M22. Then you will use the demodulator corresponding to the, if you are using AM modulation at the transmitter, then you will use AM demodulator here, and then you will be able to reconstruct your signal back. So since we are interested only in multiplexing and demultiplexing, so that is why we are just seeing the modulated signal, how you can again get, how can you can separate them out, right? You can separate these two modulated signal at the transmitter, at the receiver. So this is called demultiplexing. ठीक है? So you can also put modulator here instead of multiplier. You can just write it modulate. M1T, you modulate it and then you transmit it over the channel, and then at the receiver you put a band pass filter and then you demodulate it and you get the message. So here we should write the modulated signal. Modulated signal. So if this is X1T, this is X2T, which is modulated signal, then the output of your multiplexer will be. So don't confuse with the notations. X1T, X2T. ठीक है, ये तो क्लियर हो गया ना? कोई डाउट है इसमें?
No, sir.
Okay. So हो गया ये frequency division multiplexing. Then you can come up with a different idea that we can do something interesting, and we can subdivide the channel. If you are given a time duration of t over which you are allowed to communicate, and there are two signals M1T and M2T which you want to transmit, so you can first divide your channel in time, and you will say that these times, like all the odds time slots, all the even time slots will be provided to M1T, and all the odd time slots will be provided to the message signal. What I mean is, this is your signal M1T and this is your signal M2T. So instead of transmitting this signal for all the time and also transmitting this signal for all the time, what we do, we first sample it at various time instant, at various specific time instants. ठीक है? So for example, you are first sampling your message signal M1T at 0, TS, 2TS, 3TS, and 4TS. Similarly, you are also sampling it over, you can also sample it over the same time, and then you can shift a bit. So you just sample, we sample our signal M1T, and then we transmit first sample of this signal at this time, and the second sample we transmit with some delay. Okay, and though the sample duration is same, you are also having the same sample duration for this message signal, but because there is a time distance between, which there is a time gap between that, right? So you first send this sample, then you send this sample, then you send this sample, then you send this sample, but there is a time gap you have, so you can utilize that time gap and you can send some other signal over these times, over this time interval. So this is called time division multiplexing, and process of putting the other signal in between the first signal is called interleaving. So you interleave the message of other signal, and by this way you can now transmit two signals over the same frequency, though these samples which you transmit. So if this is your M1T, and the sample version of M1T is M delta 1T. Similarly, M2T is this, and the sample signal, after you sample it, it is called M delta 2T. M delta 1T and M delta 2T might have the same spectrum, but the time, the samples at which we are sending its values are different. So that is why it is called time division multiplexing. So you see that when you say we are going to use time dividend multiplexing, you can say now you don't need the value of your message signal at each time interval, at each time instant. Do you agree with that? You only require the values of message signal at some specific time instance.
Yes.
Yes. So that is why we call it a discrete time signal, right? Because you don't know, you don't define what is the value of your message signal M1T at these instants. So this is a discrete time signal. So we can use TDM for digital case. Digital is discrete plus we also quantize. Discrete means we are quantizing its time axis. Plus, when we also quantize this amplitude axis, it is called digital. So just for now, just you understand it as discrete. So just we will discuss. I mean later what is digital. So you can understand for now that TDM can be done for the discrete time of signals, right? Because this is a discrete signal. Then you can argue that, sir, will be able to perfectly, because are we losing something? Because you are just ignoring the values of your message signal M1T or M2T as these time instants. So answer is if we intelligently sample our signal, then we will not lose anything. ठीक है? तो अभी क्या किया अभी तक हम लोगों ने अभी हमने किया कि for continuous signals we can do FDM, and this is one way of doing multiplexing. And if we can do another multiplexing that is called TDM or time division multiplexing, and for that we are converting our message signal from continuous time to discrete time. ठीक है? So continuous time signal का क्या मतलब है? They are defined at all time instants, correct? But discrete means they are only defined as at some specific instance of time. And this is called sampling. Okay. So let's understand what is sampling. So if this is your message signal MT, and these are the time instants 0 TS, 2 or 3 TS, it is called sampling interval. ठीक है? So the value of your signal at, and you can also say 0, and it is, if it is zero point 0.6, for example, t is equal to 0 is 0.6, and it can be also at minus, so m at minus ts 0.2. So now you don't know what is the value of this signal between minus ts to 0. So they are not defined, right? So this is a discrete time signal, right? So you are converting a message signal to discrete time signal, and it is called sampling. And what is the sampling frequency? Sampling frequency is 1 by ts. So these are the two terms, sampling interval and sampling frequency, and this is the process of sampling. These things I have already told you, that this is a sampling process. So now, how can we see this sampling process? And one more thing, just assume that your message signal MT has a bandwidth MT is a continuous time signal with bandwidth B hertz. Bandwidth is B hertz. So you can think, I mean, you want the samples, right? But this is all the decision. I mean, uh, if you visualize it, you can think this process of sampling as the multiplication of your message signal with the impulse train. Correct? If you multiply your signal with impulse train, such that this impulse train will have strength as the value of that message signal at that time instant. See, every impulse has two property, right? Its location and its strength, right? So now this is your impulse train, periodic impulse train. So you can think your sampled signal. This is called ideal sampling. Correct? If we go back a bit, what we have started, we said we can do time division multiplexing by sending the information over a discrete time instance. But how will you do that? You are not going to do that. I mean, in theory, you have to take some signal, right? Some signal. You have to take some signal. So let's say we are taking impulse. We have to take, these are called pulses. We have to take some pulses in order to transmit these information, these values. So first we take an ideal pulse, let's say, that is impulse. Though it is theoretical, but it will give you many insights. So first of all, we are taking an ideal pulse, that is impulse, in order to transmit those values of your message signal which we have sampled at these time instants. So this is your sampled, and yeah, this is called ideal sampling. Just remember these words, ideal sampling. Since we are using an ideal pulse, that is impulse, in order to extract these values. Okay? And mathematically, how can we write the equation of this impulse train? Del t plus del t minus ts plus del t minus 2ts plus del t minus 3ts. Similarly, del t plus 2s. So these are the summation of many deltas. So you can write it like this. Summation del t minus nts. Okay? So the sample signal is multiplication of your message signal with the impulse train. This is your impulse train and this is your message signal. You multiply it, you get the sampled signal. So you can write all of this like this. This is nothing but the nth sample, nth impulse whose strength is equal to the value of the masses at time t equal to nts. So if this is your nth impulse, so this is the mnts or mnts. This is your nth impulse whose strength is equal to mnts and location is at nts. So this is the summation of all those impulses. Okay? So the sample signal is this ideal sample signal. So this is the just whatever I have told you. The sample signal is a sum of delta functions that have magnitudes equal to the value of mt at the time instance that the delta function occurs. Is nothing but location of delta function. The pictorial representation is this. Okay? So this is nothing but time domain representation of sampling, right? When you sample in time domain, your sample signal will look like this, right? Next. So here we have assumed ideal sampling, but in practice, we cannot generate a ideal pulse, right?
Yes.
So in order to solve this problem, we use pulse rectangle pulse of type this. ठीक है ना? Because that pulse are physically realizable, practical. So first we have understood the ideal sample signal and we have seen it in time domain. But if you want to transmit those values, since we are cannot generate ideal impulses, we have to take help of some practical pulses. So one such practical pulse is a rectangle pulse, whose width is capital T and which capital T is such that it is quite close to Ts. So now your practical sample signal will look like this. And this is called PAM, pulse amplitude modulation. Why we are calling a pulse amplitude modulation? Because we are changing the amplitude of the pulse as according to the value of your message signal. That is why it is called pulse amplitude modulation. Because modulation is nothing but changing some specific parameter of your pulse or your carrier signal. In continuous case, which we have done in AM and FM, we change either amplitude, frequency of your carrier signal. But here, since we are taking pulses, that's why we are calling pulse amplitude modulation. It is amplitude modulation, that I agree, because we are changing the amplitude of your carrier signal. But the carrier signal specifically here are pulses. That is why it is called pulse amplitude modulation. So practically, ideal sampling is not possible or impulse based sampling is not possible. So we take help of the practical pulse. One such practical pulse is rectangular pulse. Okay? These 2 points we have discussed. This is your sampling frequency or sampling rate, which is 1 by Ts, and Ts is nothing but sampling time interval. Yeah. So here what we are doing, we are changing the amplitude of the pulse, right? But we can also do two more things, that we can change the width of your pulse or the position of the pulse in order to send those values at these time instances. So according to that, we can classify our pulse modulation by two other methods, that are pulse width modulation or pulse position modulation. But we will discuss more in detail PAM, and I will just give you a hint of PWM and PPM. So let's go to PAM. So this is your PAM signal, correct? This is your sampled signal. This is your PAM signal. So we are sampling it with pulse of duration t at each nts. ठीक है, so this is your PAM signal. These are just some points. The nth pulse is from nts to nts plus t. It's very obvious. And amplitude of the nth pulse is nothing but the value of that message signal at nt is equal to nts. Very obvious. Yeah, one more point. If somebody asks you how can you generate such a signal, such pulses practically, so you can say just we will use sample and hold circuit. Why we are calling it sample and hold circuit? Just focus it here. If you want to generate a pulse, what you do, you just sample it, or you put a switch here. You switch it on, and for some time duration the switch is on. You are holding the on state of a switch for some moment. That is why, and so it will give you this type of PAM signal, right? So PAM can, I mean, network guy can call it that you are doing a sample and hold. You are nothing. You are doing nothing. You are just doing sample and hold. So you say yes, I am doing sample and hold. ठीक है? So in order to generate a PAM signal, you can do that. You have to use a sample and hold circuit. As a communication engineer, as a mathematician, you can say, yeah, this is a train of pulses where the pulses are have duration t. We are using pulse of duration t at each time and is equal to ts, and the value of each pulse changes as according to the value of the signal at that moment. But a network guy can say, or the circuit guy can say, you are doing sample and hold. So you say, okay, it's not a big deal. ठीक? So amplitude of the pulse at NTS is modulated by the signal value at t equal to NTS. So it's okay. It's just a point. So in time domain, how can you write your PAM signal? You can write your PAM signal like this. This is a pulse at t is equal to NTS. This is the pulse, right? Which we are using. So your PAM signal is nothing but, pictorially your PAM signal is this. And mathematically, your PAM signal is this. MNTS PT minus NTS. You have to just replace your delta signal with the, you are replacing your delta with P for PAM mathematically, yeah, right? Because your pulse is not ideal impulse, but it is a practical pulse, practical rectangular pulse. And we also call it a flat top sampling. That was the ideal sampling. This is a flat top sampling because you see that the top of your samples are flat. That is why it is called flat top sampling. In detail, you will study in the next, digital communication course. But just remember, this is a flat top sampling. I can ask a simple 1 mark question from this. That your PAM depends on flat top sampling. Okay, so this is your PAM signal. That I agree mathematically. One can also see this PAM signal as a ideal sample signal convolved with the filter, LTI filter, whose impulse response is PT. Let's see how. So you remember this is the ideal sample signal, right? The statement which I made, I said the PAM signal can be also seen as a ideal sample signal convolved with the linear LTI system with impulse response as PT. So if this is your ideal sample signal and you pass it through a impulse response, LTI system with impulse response PT, then it is nothing but M delta T convolved with PT. That you agree? Now you just put these values, convolved with PT, you see it is nothing but a PAM signal. So hence proved. That mathematically you can see A PAM signal, as a first you take your message signal, you are just ideal sampling it and you are generating it. So by using sample and hold, you are just coming from here to here. That I agree practically. But a mathematician, mathematically, you can also see that it is nothing but you're first converting your message signal. You are using an ideal sampler, and then you are passing it through a filter of impulse response ST. ठीक है ना? It will help you in analysis many ways. सो यहाँ तक कुछ पूछो, कुछ डाउट हो तो इसके बाद अपन शिफ्ट करेंगे स्पेक्ट्रम ऑफ सैंपल सिग्नल में. टाइम डोमेन में देख लिया both PAM and ideal sampling. अब now we will see the spectra of these two. I mean, we'll see in frequency domain how these signals would look like. ठीक है. So कोई डाउट है आदित्य?
No, sir.
Okay. Kumar?
No, sir.
Okay, great. So this is your PAM signal, that you agree, right? The ideal sample signal convolved with your PT.
Yes, sir.
So in frequency domain, why I did this, why I wrote this like this, why I just took all the pain to write our message signal, our PAM signal as a convolution of your ideal sample signal with PT, because it will help you in when you analyze it, you see how the spectrum of this sample signal will look like. So the बताओ Fourier क्या होगा इसका? Because it is convolution in time domain, it is nothing but the multiplication in
Fourier.
frequency domain. So let's first study the Fourier spectra of this signal, ideal sample signal, and it is nothing but multiplication of the spectra of the pulse used. Correct? So it will help you in this way. So let's first study the, and when we study the spectra of the sample signal, it will give you also an important question. It will answer one important question which we asked from, I mean, at very initial stage of a lecture, that if we sample a signal at different time instant, are we going to lose something at the receiver? Or how intelligently should we choose these values of TS so that we don't lose anything? So these are the questions we had in our initial discussion. So when we study the spectra of these PAM signal through the spectra of the ideal sample signal, these questions will be naturally answered. Okay? Let's see it how. Just let me know if you have any question or any doubt. Huh? So this is your ideal sample signal, that you agree, right?
Yes, sir.
So if your message signal is like this, I told you your message signal has a bandwidth of B. So this is the spectra of your message signal. So if you remember the convolution operation, or let's take a new page. What we did, we multiplied in order to get the ideal sampled signal. We multiplied this empty with the impulse train. This is impulse train. This was your message signal. So convolution in time domain. Sorry, here we multiplied. Multiplication in time domain is convolution in frequency domain. So you have to multiply your message signal convolve your message signal spectra with the Fourier of impulse train with period Ts. That you agree?
Yes, sir.
And from your signal and system course, you know the Fourier of impulse train is a impulse train. Correct? If you know, if you don't know, just recall it, go and see from your. But if you just impulse train, the Fourier of impulse train is an impulse train. And you know that when we convolve a signal with the, if you convolve a signal with a delta signal, it will just shift your signal. It will shift, excuse me, just understand the concept. This is your MF, right? Plus B minus B. Now you are convolving your this signal with the impulse train, because I give you this hint that impulse train in time domain, the Fourier of the impulse train is also a impulse train. So convolution with any delta function, if you remember, I have told you many times, will shift your signal, right?
Yes, sir.
So it will just shift your signal to some frequencies, and that will depend on the location of the impulse, the impulse train you are generating, because Fourier of impulse train is also an impulse train with some other period, with period. This is the question: with what period and with what amplitude? Because this is the impulse train with period ts and magnitude 1, or not magnitude, strength 1. तो इसको आप एक बार देखना कैसे निकालते हैं. I will just write the, I think I have made a slide now. Yeah. So the impulse train has 1 by ts, strength is 1 by ts, and period is also 1 by ts, which is fs. So अभी क्या हो जाएगा? You will shift your message signal if magnitude is 1. So the Fourier spectra of your ideal sample signal would look like this. That you agree? Because your impulse train is 1 by ts, 2 by ts, and the strengths are 1 by 2s. This new impulse train, whose strength is 1 by ts and the location is 1 by ts. ठीक है? So 0, 1 by 2s, 2ts, 3ts, 3 by ts. So now you have to convolve it. So you will shift this signal at this 0, at 1 by ts, similarly here also. So if you plot it properly, your sampled signal, ideal sampled signal, the spectra of the ideal sample signal would look like this. अब देखो, अभी समझ में आ रहा है? 1 by ts is nothing but fs that I have told you, the sampling rate or sampling frequency. So अब मुझे ये बताओ कि if you want your message signal to be recovered at your receiver, these two shifted versions of message signal, message spectra, should not overlap. Then you can put a low pass filter and you can ideally, theoretically at least, can reconstruct your message signal MF, because this is MF and this is the shifted version, right? This is your MF, right? And these
Yes.
are the shifted versions. So you are interested here to extract in extracting this signal. So you will put a low pass filter. So these two spectra, the shifted spectra and the original message spectra, must not overlap. We also call it, there is a technical term for that. But Lehman can also say that these two knots should not overlap. So क्या होना चाहिए? Condition बताइए. If this is B, this is B, and this total is Fs, अब बताओ. You want a condition that there is at least this value is positive. There is some gap.
So f is greater than 2vs.
Very good. So Fs should be greater than 2B. This is called
Thank you,
no
sir.
aliasing condition. Otherwise, there will be overlapping and there will be aliasing. Just is a term, just remember. हाँ
सर इसको नाइक्विस्ट फ्रीक्वेंसी भी बोलते हैं ना सर?
हाँ गुड. तो आप लोगों को पता है क्या ये सब?
सर एक बार पढ़ाया गया था एसएनएस में थोड़ा सा.
Okay, so you should. Okay, then you know it's good for me. Then I will just quickly. So condition for no aliasing is that Fs is greater than equal to 2b. ठीक है, तो तुम्हें पता लग गया कि नाइक्विस्ट ने कोई बहुत बड़ा काम नहीं किया. ही जस्ट स्टडीड दी spectra of your ideal sample signal and said theoretically Fs should be greater than 2b if you want to perfectly reconstruct your signal. So at in time domain, though you are only taking the values of your message signal at discrete time instances, you are ignoring the interval between 0 and 2 ts, 2 ts, ts and 2 ts and so on. But you are not losing if your rate sampling rate is greater than the twice of the bandwidth of your message signal. ठीक है, तो दिस इज द कंडीशन फॉर नो एलियासिंग, जस्ट रिमेंबर इट. तो फिर नेक्स्ट क्या था हमारा एम? सो हाउ योर पैम सिग्नल स्पेक्ट्रा वुड लुक लाइक, बताओ. ये तो हमने बहुत इजीली देख लिया था वहां पर ही कि द स्पेक्ट्रा ऑफ योर पैम सिग्नल इज नथिंग बट spectra of your ideal sample signal multiplied with the spectra of your pulse. So now we know this and our aim is to know this, to derive this. So if you took the pulse as a rectangular pulse, you know the sinc and rectangular relation of sinc and rectangular function.
Yes sir.
Okay, so if you remember, this is the pulse whose spectra is a sinc, right?
Yes sir.
So this pulse which we are using is nothing but a delayed, if you delay it by t by 2 or you shift it by 2 by 2. So pt is nothing but p1t minus t by 2. That you agree? pt is nothing but p1t minus 2. You are shifting it to the left.
Yes.
So since you know that the spectra of your, okay, so if P1T has a spectra P1F, that you know, right? The spectra, if this is nothing but T sync FT, ठीक है? That you know. So shifted का कैसे निकालोगे? You will use the property that P1T minus, if the Fourier of P1T is P1F, then Fourier of P1T minus T by 2, इसको T by 2 कर लेते हैं, will be nothing but P1 multiplied with T. Correct? So now you know the spectra of your pulse. So spectra of your pulse is T sync Ft multiplied with e to g of t. ठीक है ना? यहाँ तक बताओ, कोई डाउट है?
No sir.
Okay. So what would be the magnitude of the spectra of your pulse which you are using? It is 1. So it will be. So if you are in many cases we are only interested in magnitude. So I am writing it as explicitly here. You can take t as outside also because t is always positive. ठीक है. So pictorially, this is mathematically we have written the spectra. So if you plot the magnitude, or only if you are interested only in magnitude, then it will be like this, right? Because we'll negate the magnitude. तो देखो ये क्लियर है. And the zeros are at 1 by 2, 2 by 2, 3 by 2. This is the property of sync signal, right? Sync ft. So I have written sync ft. So this is the magnitude of the spectra of your pulse which you are using. सो एक चीज आपको याद है कि yeah. I already told you when we defined the rectangular pulse, the duration of the pulse is quite low as compared to the, where did I define it? Yeah, as compared to the sampling interval. So the pulse duration is quite low or quite less than the sampling interval. If this is true, what do you think the this will be true? बताओ. So if your t sampling interval is 10 to the power minus 2, your t will be great, because ts is quite large. If it is 1 millisecond, because it will be millisecond. So t, as compared to t, as compared to 1 by ts, your 1 by t will be very large. So this is the main thing. That you agree, right?
Yes, sir.
So अगर ts मिलीसेकंड में है तो ये किलो हर्ट्ज में हो जाएगा 1 by ts, 1 by minus 3. So 1 by t will be more than 10 to the power 3, right? It will be in kilohertz. I mean, if it is in kilohertz, it is 1 kilohertz. So your this frequency, or you can just consider it as a sum, because 1 by t is nothing but frequency. It will be quite large as compared to 1. Why I am doing this? Because I wanted to plot or multiply these two, right? Our aim was to evaluate the spectra of your PAM signal, which was nothing but multiplication of the spectra of ideal sampled signal with the pulse. So since I am only interested in magnitude, so I'm just considering magnitudes. So since the first zero of this is at 1 by t, and 1 by t is quite large to 1 by ts, so this is 1 by ts. So how your sync signal would look like this? Do you agree? Because 1 by t is very large as compared to 1 by ts. So the multiplication of first, this is your mf, right? This is the shifted version of mfs. So it will be only multiplied with the first lobe of your sync function. That you agree? And this condition will make sure that your mf will be multiplied with the first lobe only. Because we want to plot it pictorially. So pictorially, if you see your PAM signal, the magnitude of your PAM signal would look like this. T m delta f sync ft. Because this is your PAM signal and we are only taking magnitude, so it will be like this. So this would be the spectrum of your PAM signal. This is distorted, right? Because the ideal, when you ideally sampled it, the spectra of your ideally sampled signal was this. But practically, it means you are using pulse, a practical pulse, PAM, then the spectra will be a little bit distorted. That you agree? Because it is not perfect. This was your empty, right? This was your empty. And why these lobes are having less values? Because when we multiplied, the value of this is quite less as compared to this. So we are just multiplying these two. So this is the ideal sampled spectra of your ideally sampled signal, and this is the spectra of your PAM signal. So what you observed by when I mean, after observing the spectra of your PAM signal, you can make 2 points. You can make note of 2 points, that the spectrum is distorted and the peak amplitude is decreasing. This is the peak amplitude is decreasing. That you agree. And these points you can put, right? 1 by 2s minus 1 by ts. And there is a space. If there is no aliasing, there will be space, right? So this is that space. Now the question is how to reconstruct your PAM signal. In order to reconstruct our ideal sample signal, you put this low pass filter, right?
Yes, sir.
And if there were no aliasing, you can put your low pass filter at frequency fs by 2. Since you remember, for no aliasing, the condition was that your fs is greater than 2b.
Yes, sir.
And in order to get your signal back, whose bandwidth is b, you can always take a low pass filter with cutoff frequency fs by 2, which is greater than b. ठीक है ना? So we choose a low pass filter with cutoff frequency fs by 2. Of course, ideally your characteristic will be something like this. And fs by 2 पे 3 dB cutoff set कर सकते हैं. So this is okay. That I just say that we will use a low pass filter with cutoff frequency fs by 2 in order to get the ideal sound when we want to reconstruct the original signal from the sampled signal, which was ideally sampled by using the impulse train. But if you use the rectangular function, this is nothing but which I have explained you. If you are using a PAM signal, or you have sampled your signal using the rectangular pulses, then if first you put a low pass filter, but since this is distorted, what you can do, okay, just see the formula. M PAM F is M delta F multiplied with PF. So if you multiply it with 1 upon PF, then you will get the first you pass it through the low pass filter. So you get this type of signal, right? Next, you multiply it with the reconstruction filter, or a filter whose frequency response is 1 upon PF for frequency fs by 2 to minus fs by 2. And since you know this was your pulse, right? So this was your PF. Okay, pictorially let us see it. Since this was your PF, this was your synchron. So if you invert it, it will be something like this. So we have just plotted this in time positive axis, because 0, it is 0 otherwise. So this is the spectra of your pulse, and what you are doing, you are making a reconstruction filter over this frequency range, so that you can invert or reverse the effect of this. The multiplication of this only was making this distortion, right? This distortion was because of the multiplication. Otherwise, you can perfectly reconstruct by passing it through low pass filter. Okay? So you can pass it through a low pass filter, and then you can invert or reverse the effect of PF by multiplying it with an equalizer or reconstructive filter of impulse response or frequency response 1 upon frequency response, not impulse response. Frequency response is equal to 1 by PF. So it is just for understanding. So, I mean, pictorially, your reconstruction filter, the response of your reconstruction filter would look like this. ठीक है, देखो यहाँ तक बताओ. तो हम लोगों ने पैम पढ़ लिया, आइडियल सैम्पलर पढ़ लिया, और देख लिया कि उनका स्पेक्ट्रा कैसे होगा. हाउ कैन वी रिकंस्ट्रक्ट दिस थिंग? वी ऑल आल्सो सी. Just ask question if you have any till now. So you can do TDM, right? By sending PAM signals of two different message signals, right?
Yes, sir.
Okay. So as I told you that we can also do something interesting. Sometimes, as you remember, the amplitude of a signal, if you transmit amplitude, your message over the amplitude, then the noise affects it more, because noise affects the amplitude more, right? So in
Yes, sir.
many cases, you are not very. I mean, when your channel is bad or your the conditions are not good where which you are sending the information, then you sometimes use some other methods also. You can use, right? So there is one technique where you can send these samples because our aim was to send these samples, right? We can send these samples by using the width, by varying or by changing the width of your pulse. That is called pulse width modulation. So let's see how can we generate a pulse modulated system or pulse modulation scheme from the PAM scheme which we have already studied. ठीक है. So पहला स्टेप क्या पढ़ो? Step 1 is पढ़ो आदित्य.
Generate PAM.
Okay. What is the second step?
Generate sawtooth waveform.
Okay. So you can generate a sawtooth waveform like this. How you can do that, we are not going to discuss. But this is a sawtooth waveform. And if this is a pulse, then this will be sawtooth waveform with some amplitude, and the duration will be same as the duration of your pulse used for the PAM. So this is your PAM signal that you agree in white.
Yes, sir.
Next, you generate a sawtooth waveform like this, and then you पढ़ो.
Add these two waveforms
Okay, add them.
and then pass through comparator.
Okay, so after adding your signal, if this is your x1t, just or xpam t, you can write xpam t, and if this is uh, you can give any name, sawtooth है ना, तो xst or xsaw. So when you pass these two pulses, two signals, first is PAM and second is sawtooth. Subsaw. You can write X subsaw, or you can use some any other, or you can use M also. If you, we have used M everywhere, so you can use M also. So just right. You can replace it with M. It's not a big deal. So once you summate, the summation of these two waveforms would look like this. ठीक है. अब बताओ, the next step is pass it through a
Comparator.
comparator. So it's a four-step process if you want to generate a pulse modulation scheme. So you have to pass it through a comparator, and at here we provide V. So whenever your input to this signal is greater than V, it will give you 1, and if it is less than V, it is giving 0. So the output of comparator XOT is this, and if this is the X, just name it X MPAM T plus M SAW T, and this is the added signal M added T. So when your M added signal, when your added signal M sub add T is greater than V, we get 1. उल्टा लिखते हैं generally. 1 second. 1 when your M add T is greater than V. 0 when M add T is less than. Otherwise also you can write. So how would your PWM signal would be? How you get the PWM, that the width of your signal would be varied or modulated according to your message signal. For this, if this is your V, if this is the threshold which we set at the comparator, it will give you 1 for this time instant, right? It will give you 1 for this time instant, for this sampling interval. Here you see the width will change according to the values, because your sawtooth wave is little below to this sawtooth wave. So the value, the width of this will be more as compared to width of this. Similarly, the width of this will be further less. So as you can see, If you just plot it correctly, very nicely, you see just for this time up to this time instant, you get a, so the width of your first pulse will be this, or yeah, you used the width of your second pulse will be this, the width of your third pulse will be this, the width of your fourth pulse will be this, sixth will be this, and so on. So as you see, as the magnitude reduces, the width will also reduce. If you draw it nicely, you will see that. So if you have any doubt, you can ask. So this is how you generate a PWM signal. It's a four-step process. You generate a PAM, you generate a SAW signal, sawtooth signal. Why we are calling it sawtooth? Because if you see this saw, I mean these are the tooths, it looks like a saw. And we add these two waveforms. You know RE we use, that is why. So then it passes it through a comparator and we'll get this pulse width modulation. So in pulse width modulation, the width of your pulses carries information. The height is same as for height. Height of the pulses are same. Height is same. And pulses are always centered at sampling instant NTS. So we can say that they are centered like this. Similarly, I told you we can also do something that we can pass these samples over the position of the pulses. I mean, the position of the pulse decides the value of your message signal at those particular time instants. So this is called pulse position modulation. And in pulse position modulation, the information is carried in the position of the pulse. Height and width are same. And here the pulses are not centered at the sampling intervals, sampling instants. Of course, they can't be right. Because here we are arguing, though I'm not going in detail, and I encourage you to read ppm. So this is the sampled values, and we are saying that the position of the pulse will decide the magnitude at these time instants. So this is the time interval 0 to ts, right? So we'll see the location of the pulse, and according to that we decide the value of the message signal. So I do not want to go in much detail, I just give you the idea. So this is the pulse position modulation. And each of these schemes have some advantages and some disadvantages. And if you want to just understand one particular case where PWM and PPM are advantageous over PAM, you can give me just, can you give me one example? Just you just read it and just tell me. See, if your time channel is varying, your gain is varying with time. And if you send your PAM signal, the magnitude of the received pulses will be changing, right? And it will affect the demodulation process. But if you are not, if your message is not, information is not in the amplitude, then variation of the channel will not affect the demodulation process. So this is the one advantage. There are many other advantages, like if you can compare your PAM and PWM and PPM with respect to bandwidth. You can see which of them occupy more bandwidth, then accordingly you can choose. You can also see whose demodulation is less costly, whose modulator are more costly. Of course, PWM will be more costly, right, in terms of transmission, because you are generating your PWM after your PM, right? So
Yes,
these
sir.
are the some advantages and disadvantages you can see from your book that I'm not going to discuss. So if you want to ask anything, you can just ask. And give me one practical application of sampling. TDM, right? We can do TDM.
Yes, sir.
हाँ तो कितना टाइम हो गया?
सर 3:10 हो रहा है.
3:10. So it's good that we finished in 1 hour. It's good. I like this. I mean, so do you have any question?
No sir.
Okay. Only two of you were here there.
नहीं सर, 2-3 लोग और थे, वो अभी कुछ देर पहले चले गए।
अच्छा वो चलेगा